So now that we're familiar with both the size and the power of a hypothesis test, we're going to look at the power function. Yes, it's useful to know what the power of a test is going to be. So that's the probability of accepting H1 when H1 is true, or rejecting H0 because H0 is false, so correctly rejecting H0. It's useful to know that. And so far, you've been given a new parameter and you've been able to calculate the probability of that correct rejection using the new parameter. In actual fact, it would be very unlikely that you would immediately know what the correct parameter is after realizing the one you'd chosen to use was incorrect. So we need to be able to get an expression for the power in general terms. We need to be able to generate a function for the power, which we can then later on substitute different values of the parameter into. So this would be the power function, a function in general terms to represent the calculation for the critical region in a hypothesis test. Okay, I'll show you in an example. So here we're told that past experience has shown that the number of accidents that take place at a road junction has a Poisson distribution with an average of 3.5 accidents per month. So that's the lambda that we're going to use originally. A trading estate is built alongside one of the roads leading away from the junction, and the local council is anxious that this may have increased the accident rate. To see if the number of accidents has increased, a test was set up with the null hypothesis lambda equals 3.5 and the alternate hypothesis being accepted if the number of accidents within the first month after the alteration was greater than or equal to 7. So there we're actually given the critical region. Greater than or equal to 7 is the critical region. Okay, it's a lot of information there, but to sum it up, we have a parameter for the Poisson distribution of 3.5 per month. We have a critical region where x is greater than or equal to 7. We need to try and calculate the size of the test, and we're going to generate a power function. So they've given us the null hypothesis, and the alternate hypothesis we can tell is going to be that lambda is greater than the 3.5. Critical region, let's get this down, x is greater than or equal to 7. So the first thing that we're asked to do is to calculate the size of the test. Now we know the size is the critical region using the original parameter, the probability that we reject H0 when we shouldn't have. In this case, it's going to be the probability that x is greater than or equal to 7 using the parameter lambda equals 3.5. Just before we get to our calculators, let's rewrite that as a 1 minus the probability x is less than or equal to 6. That's what we need to find. On our calculators, PCD 0.6 and that gives us an answer of 0.0653. So that's the size of this test. Let's go for the power function. Now the power once again is the critical region, but this time using the new parameter. That new parameter is unknown at the moment, but we can still use the probability function to generate an expression. Let's see how that happens. Now, we want to find the probability that x is greater than or equal to 7. We're once again going to use a 1 minus technique. So it's 1 minus the probability x is less than or equal to 6. Now lambda is unknown, so we're going to give this probability in terms of lambda. So 1 minus less than or equal to 6 is the same as the probability of x equaling 0, plus the probability x equals 1, plus the probability x equals 2, and so on. Each of these we can give its original form. We're going to be using e to the negative lambda, lambda to the power of x over x factorial. So this was the probability function for the Poisson distribution. So we'll substitute 0 for the first term, we'll substitute 1 for the second term, substitute 2, all the way up to e to the negative lambda, lambda to the power of 6, all over 6 factorial. Now, this is the power function, but we can definitely tidy this up. We'll be expected to show a simplified version. The very first thing I can see is that I can factorize out e to the negative lambda. That appears in every single one of these 7 terms. What am I left with? Lambda to the power of 0 over 0 factorial is 1. Lambda to the power of 1 over 1 factorial is lambda. And then from here, we get this sequence. Lambda squared over 2 factorial. Lambda to the power of x over x factorial. Okay, now this is simplified about as far as we can go, and this would be the power function, where if we now gave you a value for lambda, you would be able to instantly find the power. So if lambda equaled 2, if lambda equaled 7, if lambda equaled 50, you can find the power. So let's try that out. When lambda equals 4, just in your calculators, you'd get a power of 0.1107. When lambda equals 5, you would get a power of 0.2378. And when lambda equals 6, you get a power of 0.3937. So this is how we use the power function, and we start to get a value for the power for different values of lambda. We're actually asked to graph this power function. So for each new value of lambda, we could plot what the power is going to be and try and see if there's any trend that we can follow in the graph of the power function. And here's what this graph would look like. And we could see that as the parameter increases, the power increases as well. As the true parameter increases, the probability of us getting a correct conclusion to reject H0 within our original hypothesis test increases. So this is the power function, just a way to show in general terms an expression which we can substitute into to generate the power of a test.